Hey guys, and welcome to episode 10 of Scientific Drinking. Tonight, if someone asks you,
when did you become an expert in thermonuclear astrophysics?
You'll be able to answer them
last night.
Because tonight we're talking about stellar life cycles. Cheers. All right, so it's a pretty big topic. What provoked this episode was recent news about Betelgeuse's impending explosion as a supernova. And that's been floating around the internet for a few days now. It's gotten a little bit out of hand, maybe to the point of just being hyperbole. And I'll tell you why at the end of the episode. We gotta lay the foundation so that makes sense. And the foundation of that is thermonuclear astrophysics. Speaking of something completely different, tonight I'm drinking Screamin' Reels IPA. Explore the depths of beer, apparently. Could be a lot deeper. Tropical bitter hoppy IPA, not bad. I mean, it's an IPA, right? So there you go. So let's start at the basics. What is a star? Well, a star is a collection of gas that is being driven into nuclear fusion via its own gravity. And that nuclear fusion is keeping it from collapsing into an even denser object. So basically, there's a balance of gravitational force pushing in and fusion heat energy pushing out. Stars form from a cloud of gas floating around in space. And when there's enough of that gas, it compresses into a star, spinning around to form an accretion disk with a protostar in the center and eventually into a solar system, like the one we're in right now. After that, the star starts burning its fuel, which initially is hydrogen. At the beginning of the universe, we had mostly hydrogen with some helium and very trace amounts of lithium, which is periodic table element 1, 2, and 3. 1 proton, 2 proton, and 3 protons, respectively. Now, when the star starts burning all this fuel, it turns 2 hydrogen atoms into helium atom by compressing it together, just by the force of gravity. This releases a tremendous amount of energy relative to the small forces you're dealing with. And so it burns up a lot of its hydrogen, and eventually when it starts running out of hydrogen, it burns helium. It presses helium together. What's 4? Oh, I need to pull up the periodic table. This is shameful. And it can put a hydrogen atom in helium and create lithium, or 2 helium atoms into beryllium, and so on and so forth. Now, it keeps doing this over eons, billions of years, depending on the size of the star, until it gets to the point where it can't burn anymore. It's just making iron. And iron does not release enough energy for the star to sustain itself. If you burn enough iron, the outer shell of the star starts to expand, growing larger and larger into what we call a red giant. Betelgeuse is a red giant. And this is the late stage of a star's life. After this, it can go through one of many different phases, depending on the mass of the star. Really massive stars collapse into black holes because the gravitational energy is too great and it crushes it into a singularity or something within the realm of the event horizon that we can't quite understand with modern physics. If it's a little bit smaller than that, it'll create a pulsar or magnetar, which is pretty much just a really dense atom, just a single atom about the size of a city. Usually pulsars are about the size of the island of Manhattan. Stars that are too small to create pulsars create white dwarfs. And our star is one of these stars that's eventually going to create a white dwarf. A white dwarf is the remnant of a stellar core. That outer shell swells up after it starts burning iron. All that drifts away into a planetary nebula, which lasts several hundred to several thousand years. If that stellar core, the white dwarf, drifts on long enough, it'll eventually become a gray dwarf, which is just the husk of the stellar core, devoid of energy, no longer radiating, and drifting on into eternity. But I digress. What we're going to talk about more is about a star's life cycle, how do you categorize these stars, and what these stars are like. Stars are generally categorized in what's called a main sequence star. There are some exceptions, just as protostars or T Tauri stars, which are very, very young stars that haven't yet formed into their final stage. Now, as you can see from this illustration, the main sequence is quite clear. Most stars lie on this kind of wandering line that is the main sequence. Categorizations are O, B, A, G, K, and then you have some brown dwarf. This naming scheme seems kind of arbitrary. Why is O the brightest star? Well, it turns out that Annie Jump Cannon, the famous astrophysicist working for NASA, looked at all these stars and decided to categorize them by their peak radiative intensity. And looking at it in the visible spectrum, it's the A class that is the brightest. But once we started looking at the stars, then it became quite clear that this wasn't quite a classification of size or brightness as a whole, because the peak radiative intensity of visible light isn't indicative of the entire spectrum. Enter the Morgan-Keeman spectral classification, which rates stars based on how hot they are. In this case, the O-type star, which is the biggest, bluest, and brightest star, is the hottest. Now, this kind of bright light can be imitated here on Earth. Now, if you take a chunk of metal and you start heating it up, eventually it starts glowing orange, and then red, and then bright white. And if you kept heating that up, it would eventually burn blue. But it's really hard to dump that much energy into an item. at atmospheric temperature and pressure because it just kind of radiates and convects that heat away. See the previous episode about the spacecraft thermal control. And now that brings me to blackbody radiation. Any object with energy is going to radiate its heat out depending on its temperature, and it's going to look different depending on how hot it is. Looking at the objects around us, which are quite hot when considering the universal average temperature of a couple Kelvin, when taking the spatial average, they're quite hot. And if you look at them with the right filter, they're actually glowing. Everything around us is glowing at infrared wavelengths. Now, eventually, when you drop it down, those wavelengths get longer and longer because there's less energy being radiated out, and that energy is less energetic. The amplitude is lower. Okay, but if you crank that temperature up, it starts going from the infrared into the red, into the visible, hence heating up that sample of iron or that block of anything, and eventually gets blue bright, and then gamma radiation all the way up there. Now, there are a few special cases that we're going to touch on, and this is eventually bringing us to the case of Betelgeuse. This first of these cases is VY Canis Majoris, which is the largest star ever discovered. Absolutely huge. In fact, it shouldn't even exist because it's just too big. There's too much mass. It should have collapsed. But nevertheless, it's there. It's a red supergiant, much larger than any other star we've seen. I'm sure maybe you've seen some illustrations out there comparing VY Canis Majoris to other stars, all the way down to our own solar system, which is just minuscule by comparison. Most stars aren't like that. Now, I already covered pulsars, and pulsars and magnetars are super dense stars, and the only thing that's keeping them out is the strong nuclear force and its angular momentum, which is spinning so rapidly that it's almost near the speed of light. And it slows down very slowly. It's called a pulsar because at the poles, they're radiating all this electromagnetic energy, and if we look at it just right, they'll sweep by the Earth and we can see it as it spins, hitting the Earth at incredible speeds. The only reason it doesn't kill us is because it's so far away. Now, of course, I mentioned black holes and have a whole episode about that. That is another special case of stars. Another special case is Methuselah, which is perhaps the oldest star in the universe, but probably not because we can see it. I mean, statistically, we can't see very many stars in the universe, but we can see Methuselah. And by many estimates, it is the oldest star in the universe. In fact, it exceeds the age of the universe itself, which doesn't really make sense. So there's obviously some kind of mechanism going on that we don't understand. That compounded with the recent reduced estimates of the age of the universe, bringing it down to something like 11 billion years, makes Methuselah a curious case indeed. We can deduce that there are probably many stars like Methuselah floating around out there that are special cases, and something more is going on. The last case is Betelgeuse. Finally, we're talking about Betelgeuse in its own right. Now, at Lowell Observatory, where I had one of my internships, they are connected to the Naval Precision Optical Interferometer, or NPOI, which is a unique kind of telescope that varies the distance between two smaller telescopes to get an idea of the size of objects. Now, using this technique, they found stars like Altair, which is spinning so fast that it's oblate, much like Saturn, but to an extreme degree. And you can actually see, as it's tilted slightly towards us, that the poles are hotter than the outer shell, meaning that's spinning very fast, in fact, fast enough that it might be shedding its outer layers, which is pretty astonishing by itself. Now, they used this technique to look at Betelgeuse and found out that it's not really a round star at all. In fact, it's kind of oblate and blobby. Maybe the star is really at its late stages in life. But keep in mind that when you're talking about stellar lifetimes, you're talking about billions of years, sometimes hundreds of millions in the case of the brightest, hottest stars, because the brightest, hottest stars burn more energy faster and live shorter lives. Live fast, die hard.
Oh yeah, that sounds good.
But the smaller, dimmer stars can go on for billions and billions of years, much like in the case of Methuselah. In general, Betelgeuse is not that special. It is a star somewhere in the main sequence that has lived out its life, and it's at the very end. Now, we know what these kind of explosions will look like because several thousand years ago, Chinese historians characterized the death of what is now the Crab Nebula pulsar, which was at the time a star. And that was so bright that it caused shadows on the ground at the darkest nights without a moon for several months. We can expect something similar from Betelgeuse when it does go, but like I said, stellar lifetimes are very long. The likelihood that Betelgeuse is about to explode now or any time within our lifetime is probably pretty small. It might have hundreds or thousands or tens of thousands of years left of its life, maybe even 100,000. We just don't know enough about these stars to make an accurate guess about its lifetime. But what we do know is that it is dimming. It's dimmer than we've ever seen it before in recorded history. But we also know that it is a variable star. All of these dips are periodic with different intensities. So maybe we're just seeing a new variability, a new low, many years before it ever blows up. And statistically, that's probably the case. So don't hold your breath that you're gonna see shadows at night, because Betelgeuse may have many more years to come. Sorry to disappoint you, but hey, there's many other things going on. We're going to the moon in a few years. That's pretty exciting if you ask me. Cheers.
No hard feelings, Point Break. You got a mean swing.